Let's rewind time, far beyond anything you're used to. No, even further than that. You've just plunged into Earth's ancient oceans. But instead of tiny trilobites or simple early fish darting around, you're surrounded by absolute monsters. Massive tentacled predators, longer than today's giant squids, glide silently through the water. Sea turtles weighing more than 4,000 pounds drift past like living tanks. And the fish? There's nothing normal about them anymore. Welcome to the era of prehistoric marine gigantism, a forgotten chapter of Earth's history that unfolded hundreds of millions of years ago. Unlike deep-sea gigantism, which is limited to the darkest parts of the ocean, this phenomenon took over everywhere, from open waters to reefs and even shallow seas. What makes it even stranger is that these giants didn't all grow massive for the same reason. Many of them lived in entirely different time periods, separated by millions of years, and never shared the ocean with one another. Yet again and again, evolution pushed marine life toward extreme size. So why do enormous creatures keep appearing throughout nearly every era of prehistoric oceans? And which modern animals still carry the legacy of these ancient giants today? To understand what may be the earliest example of true gigantism, we have to start with one of the strangest creatures evolution ever produced, Endoceras, the largest of the orthoconed cephalopods. And yes, at first glance, it looks completely unbelievable. Like an animal that somehow decided to wear the tallest traffic cone ever made. It doesn't look fast, intimidating, or even practical. But Endoceras wasn't a squid. It was an early cephalopod, which is why it still had tentacles, just attached beneath a massive, rigid shell. As ridiculous as it may look, Endoceras was an apex predator during the Ordovician period. And that's hard to believe, considering it seems like something you could defeat with a pencil sharpener. But its dominance didn't come from speed or intelligence, it came from one thing only: size. Most paleontologists estimate that the largest Endoceras grew to around 20 feet long, with most of that length made up of its enormous, pointed shell. Some older estimates suggested related orthocones, like Camarasaurs, may have exceeded 30 feet, but those numbers are debated and not widely accepted today. A more realistic upper limit puts them closer to 23 feet. The truth is, we'll never know their exact size. These animals lived nearly 500 million years ago, and fossil evidence can only tell us so much. What everyone agrees on, though, is that they were absolutely massive. To put that into perspective, compare Endoceras to a modern giant squid. If you ignore the squid's extremely long, trailing tentacles, most of its actual body is only about 15 feet long. Endoceras, on the other hand, wasn't padded by soft, flexible appendages. That length came from a solid, heavy shell, real, dense body mass. So who would win in a fight? Of course, these two creatures never met. Giant squids only appeared around 5 million years ago, while Endoceras ruled the oceans roughly 470 million years in the past. But for the sake of comparison, it's worth imagining what would happen if these two giants somehow crossed paths. But just for fun, let's entertain the hypothetical. Endoceras carried an enormous, rigid shell, one that a modern giant squid would almost certainly struggle to damage. These animals were incredibly heavy as well, with estimates suggesting they may have weighed close to 700 pounds. But if you're picturing Endoceras rocketing through the water like a living spear, impaling anything in its path, that's probably not how it actually moved. That towering shell wasn't a weapon. It was mainly used for defense and buoyancy control, not for charging at prey like a biological javelin. And once a fight moved past the shell and reached the soft body underneath, things would become far more balanced. At that point, it would come down to beak versus beak, with neither cephalopod holding a clear advantage. The real problem for Endoceras, though, was mobility. Carrying a massive shell made it slow and awkward, not exactly built for quick turns or fast pursuits. To do any real damage, it would have needed to physically grab the giant squid, and that's a tall order. Giant squids are among the most intelligent invertebrates alive today, with the awareness and agility to avoid a clumsy opponent. Unless Endoceras had far more muscle power than scientists currently believe, it would likely struggle to land a decisive attack. And even if it was stronger than expected, the squid could probably escape rather than stay locked in a losing fight. Ironically, this lack of speed is exactly why Endoceras was able to become so large in the first place. During the Ordovician oceans, nothing else was particularly fast either. There were no sharks, no marine reptiles, no high-speed predators slicing through the water, and certainly no giant squids. Most life moved slowly, simply, and somewhat awkwardly. In an environment like that, sheer size was enough to make you nearly invincible. Speed wasn't necessary. Agility wasn't required. You just had to be so big that nothing else dared to challenge you. That massive shell acted like a shield, protecting Endoceras from smaller animals that might try to nip at its soft head, allowing it to drift through ancient seas as an untouchable giant. But the most important thing that massive shell protected Endoceras from was other orthocones. These animals sat at the very top of the food chain, which meant they didn't have many natural enemies. In fact, the only real threat they faced was each other. The ancient seas were filled with giant cone-shaped predators drifting through the water, all competing for the same prey, and sometimes for each other. This created a brutal evolutionary arms race, but one fought almost entirely within their own group. Generation after generation, the pressure to survive pushed them to grow even larger. And food was never an issue. The Ordovician oceans were packed with slow, easy prey, giving these giants more than enough energy to support their enormous size. Ironically, the very feature that made them so successful is also likely what doomed them. That oversized, awkward shell eventually became a liability. As new life forms began evolving, especially early sharks and faster swimmers, being big and clunky was no longer an advantage. The shell made them predictable, slow to react, and easy to target. There's no elegant way to put it, a body plan that awkward is just awkward. Even though they ruled their era, Endoceras and its relatives simply couldn't compete once agile, fast-moving predators entered the scene. You might be thinking, well, apex predators are always huge. But here's the key difference: this was a world without land predators. Nothing was walking around hunting anything. There were no dinosaurs, no giant reptiles, not even early land-dwelling vertebrates. The ocean was the entire battlefield, and every major predator on Earth lived in the water. Land ecosystems simply didn't matter yet. And the ocean gives giants a massive advantage. Buoyancy carries most of an animal's weight, meaning gravity barely limits how large marine creatures can grow. Sizes that would be physically impossible on land, where bodies would collapse under their own weight, are completely viable underwater. So when the giant orthocone predators began to fade away, something else stepped in to claim the top spot. Enter the Eurypterids, better known as sea scorpions, and the largest scorpions to ever exist. Just like everything else shaped by marine gigantism, they were enormous compared to their modern relatives. The largest species, Dunkleosteus, could reach lengths of over 8 feet, longer than most humans are tall. So why did these creatures also grow to such extreme sizes? It wasn't oxygen levels. Those wouldn't peak until the Carboniferous period, millions of years after Eurypterids were already giants. Their size explosion came from the same familiar source, competition. As orthocones declined, the oceans turned into a chaotic free-for-all. Eurypterids now had to compete with other Eurypterids, early armored fish, and a rapidly diversifying cast of prey. And when everything around you is getting stronger, faster, and more dangerous, there's only one reliable way to stay on top. Get bigger. Larger bodies meant everything: more raw strength, longer reach, heavier strikes, and overwhelming power, especially in shallow seas where nearly every creature was both hunter and potential prey. In those crowded environments, being bigger wasn't just helpful, it was survival. By the time the Devonian period arrived, the oceans had turned into floating battlefields filled with heavily armored fish known as placoderms. Thick bony plates covered their bodies, jaws grew stronger, and defenses became more sophisticated with each passing generation. And when everyone around you keeps reinforcing their armor, the only way to stay dominant is to upgrade your weapons and scale up your size. That escalating arms race eventually produced one of the most legendary predators in Earth's history, Dunkleosteus. This creature was essentially the final boss of the Devonian seas. Some estimates suggest it reached 20 to 30 feet in length, with a head so heavily armored it functioned like a solid block of living steel. The evolutionary cycle was relentless. Fish developed armor, predators evolved stronger jaws to break it, prey responded with even thicker plating, and the process repeated over and over until Dunkleosteus emerged at the top. Fossils of Dunkleosteus have even been discovered bearing bite marks from other Dunkleosteus, clear evidence that these giants hunted, and sometimes killed, each other. Many of these evolutionary arms races weren't predator versus prey at all, but species competing directly with their own kind. The pressure to survive pushed them toward extreme sizes, right up to the physical limits of what their bodies could handle. And if you've been following the pattern, this should sound familiar. Again and again throughout prehistoric history, apex predators didn't rise by becoming faster or smarter, they rose by becoming bigger. Eventually, the only creatures capable of challenging them were others just like them. First, the oceans created giant orthocone predators. Then, they produced massive sea scorpions. And next, they gave rise to towering armored fish. The cycle of marine gigantism just kept repeating. In the end, almost any body design could become the top predator of its era. The key wasn't speed or intelligence, it was simply being the first to cross the size threshold and become a giant. Now let's jump ahead hundreds of millions of years. By the late Cretaceous period, the rulers of the ocean were no longer cone-shaped shells or armored fish. This time, the seas belonged to reptiles. Global oceans were vast and shallow, spreading across continents like inland seas. Warm temperatures, high sea levels, and sprawling reef systems created some of the most productive marine environments Earth has ever seen. With so much life packed into the water, predators could grow to extreme sizes because there was always massive prey available. And as more giants appeared, competition forced predators to scale up even further. If you weren't enormous, you didn't stand a chance. This is when the famous marine reptiles emerged: mosasaurs, plesiosaurs, pliosaurs, and even massive land dinosaurs roaming coastal regions. The size race reached yet another peak. And once again, this had nothing to do with oxygen levels or polar gigantism. The atmosphere wasn't dramatically different from today. Size was simply the price of survival. Even animals you'd never expect were pulled into this arms race. Meet Archelon, the largest sea turtle to ever live. This colossal turtle stretched over 13 feet long, with a shell wider than most modern cars and flippers built to cross entire oceans. Archelon wasn't oversized because of climate or oxygen, it grew massive because the Cretaceous seas were crawling with monsters, and only monsters survived. But that leads to the biggest question of all. If being gigantic worked so well, why did all of these giants disappear? And where are they now? The simplest answer is extinction. When a massive asteroid strikes the planet, it doesn't matter how dominant you are, or it resets the entire game board. Mosasaurs, no matter how powerful, couldn't survive a global catastrophe. After that wipeout, evolution had to start over. Our modern world is only 66 million years old, while the Mesozoic era lasted more than 150 million years. This time around, mammals rose to dominance. Today's oceans are colder, less productive, and no longer filled with endless supplies of giant prey. That makes it far harder for massive reptiles to survive. But let's imagine something interesting. If you dropped a group of mosasaurs into today's oceans, would they reclaim their throne as apex predators? Probably not, and food isn't the only reason. Reptilian gigantism has essentially stalled, and there are several explanations. First, modern oceans are ruled by warm-blooded hunters like orcas, sperm whales, and high-speed sharks. These animals can chase, accelerate, and maneuver in ways giant reptiles simply can't match. Second, today's ecosystems just don't support that kind of scale. Prehistoric reptiles grew enormous because everything around them was enormous: giant ammonites, giant turtles, giant fish, giants everywhere. Once that abundance vanished, the entire blueprint for reptilian superpredators vanished with it. Reptiles simply don't occupy that role anymore, and evolution hasn't pushed them in that direction for tens of millions of years. Modern ecosystems just don't reward that kind of body plan. There's also another major factor: today's food webs are far more efficient and restrictive. A reptile stretching 40 or 50 feet long would require an enormous and constant supply of energy. Unlike whales, reptiles lack thick insulating blubber, warm-blooded metabolism, and highly efficient oxygen use. That makes surviving in cold oceans, or traveling vast distances, extremely difficult. You could even add a fourth reason: humans would never allow massive marine reptiles to freely dominate the seas. But for the sake of this thought experiment, we'll leave ourselves out of it. That said, marine gigantism didn't vanish completely. It just changed. Some descendants of ancient ocean giants are still alive today, just hiding in plain sight. The leatherback sea turtle, while smaller than Archelon, can still weigh over 2,000 pounds. The giant squid continues to grow beyond 40 feet, remaining one of the most mysterious animals on the planet. And the blue whale stands above them all, the largest animal to ever exist, larger than anything the prehistoric oceans ever produced. The giants of today are different. They're more specialized, more limited, and far more niche than their ancient counterparts. We no longer see massive sea scorpions or giant marine reptiles, but the evolutionary arms race never truly ended. Giant squids evolved to grow longer and more powerful to survive against growing threats. In response, sperm whales evolved into the largest predators on Earth, perfectly adapted to hunt those same colossal squids in the deep. The same patterns are still playing out, just with different players. And if Earth ever experiences another extinction-level event, who knows? The oceans of the future might be ruled by giant dolphins. Thanks for watching.